Another more interesting talks coming up, and so the first two of them are really about searchable encryption, and the first is given by Zachary Kissel. Please.
All right, so this is joint work with Ji Wang at the University of Massachusetts. Okay, so the basic problem in searchable encryption is to assume that Alice possesses a collection of documents she wants to store in the cloud. And she wants to guarantee two following things. The documents cannot be read by the cloud provider. That's simple encryption. And she can search over the documents using some query queue without revealing the query. And that's the problem, searchable encryption. The general solutions in the literature work as follows. Alice has a collection of documents. She encrypts those documents and puts them into the cloud. She then takes and builds an index and encrypts it. This index is an inverted index in particular, and it maps queries to documents that match those queries. Okay. When Alice wants to make a query, she generates a trapdoor, sends that trapdoor to Bob. Bob uses the trapdoor and the encrypted index to evaluate which documents match the query. Those documents are then returned. Alice decrypts and knows the solution to the problem or knows the solution to the query. Okay. The primitive consists of four basic algorithms. A probabilistic polynomial time setup algorithm that takes a security parameter and returns a key whose length is polynomial in the security parameter. It takes there's a build index algorithm that takes data collection and a key and produces an encrypted index that's polynomial in the size of the security parameter. Finally, there's a token algorithm that, given a query and the key, produces a token that can be used to search over the encrypted index. The last algorithm is search. This is run by the cloud Bob. It takes as input the encrypted document collection and a token TQ and returns the matching documents. The security goal of a system like this is you want to guarantee the cloud learns nothing about Alice's queries or data except some acceptable amount of leakage. So this is an absolute security. We'll model leakage as a stateful function, and we're concerned with two pieces. What's leaked by the existence of that collection on the cloud, and what's leaked by query processing. The state-of-the-art in security for SSE is called CQA2 secure, chosen query attacks. And what this means is there does not exist a probabilistic polynomial time adversary that can compromise the system, even if they're allowed adaptive queries. And just to remind you what adaptive queries are. So we model security as a game in the real ideal paradigm. The adversary first gives the game the document set. The game produces an encrypted index, and this is tracked inside a transcript. The adversary then gives a query. The game answers by giving the search token and the results. And that gets added to the transcript. This can be repeated n times, resulting in a real transcript. Now, if we happen to be in the ideal world, we introduce a simulator. The adversary again gives the data collection to the game. The game, instead of performing any computation, forwards leakage to the simulator. The simulator then uses that leakage to produce an encrypted index, which it commits to, and that is forwarded to the adversary. On a query, the queries are forwarded to the game, the leakage to the simulator, and the simulator simulates what the trapdoor should be and what the results are. And this can be repeated n times. Then we ask the question, is the real transcript computationally indistinguishable from the ideal transcript? So in this work, our main contribution is a theorem where we show that any CQA2 secure searchable encryption system supporting keyword queries can be used to construct a CQA2 secure SSE system that supports phrase queries at the cost of some additional leakage. So to show you how this theorem works, instead of doing a proof, let's look at an example. And this is going to be based on the keyword SSE system due to cache and others, and this is CQA2 secure. So Alice runs the setup algorithm, gives the security parameter, gets the master key, which is polynomial in the security parameter. She then goes on to build the index, where she's given the DB as a form of key value pairs, where the key is a word and the value is a document identifier. Then out arrives a key value pair that's encrypted. The left-hand side is a pseudorandom label. The right-hand side is an encryption of the document identifier. These pseudorandom labels are generated by applying a pseudorandom function with keys derived as follows. So the pseudorandom function uses key KW1, which is derived from a PRF keyed with the master key. Likewise, for the encryption algorithm, we apply a key derivation function again. The C in the entry is a counter for the Wth occurrence of that keyword in the document collection. The leakage is nothing more than the number of entries. So this is minor. To generate the search token, you get a word in the master key, and it outputs the key pairs we saw in build index. Okay. To perform a search, Bob forwards the token to the search algorithm, and then generates the first pseudorandom label by applying the PRF. We then do a constant time lookup into the EDB, and we store off the matching document identifier, decrypting it. We then apply the next pseudorandom label, find that in the encrypted index, return the document identifier, and then we repeat the process one last time. For pseudorandom label 2, we find no entry, and we return the results to Bob, and those are the matching documents. Okay. The leakage here is the number of documents that match, or the IDs of the documents that match, and the search pattern, which is nothing more than the repeated documents from previous queries. Now, to do phrases, we look at a data structure for information retrieval, which is called a next word index. This next word index takes a vocab list as a linked list and stores a pointer to another linked list that matches the next words that could follow. And off each next word is what's called a posting list. The posting list starts with the number of documents that match, followed by the document identifiers, the number of entries within the document that match, and their locations. Okay? So document 9 contains one instance of W1, W2 at position 4. Now we take this next word index structure and collapse it into a DB. The keys are consecutive pairs of words in the next word index, and the values are the identifier of the document that contains the key and the location in that document. Then we'll obfuscate the word pair location information to qualitatively reduce the leakage, and then we'll construct the DB. So here's how we collapse that data structure. We notice that we have W1, W2. It occurs in one location in document 9, specifically at location 4. We look at the same with W4, W3. It occurs at 2 locations in document 3, 4 and 8 respectively, and then 5 in W4, W2, 2 in document 3, 5 and 9, and 3 in document 5, 6, 9, and 12. So now we have key value pairs. We're going to sample a key KL uniformly at random. And for all key pairs we'll update the location by tracking the next possible location. Then we'll obfuscate this by applying a pseudorandom function. And once we've done this to all documents, we'll forget that key. Now, our construction runs setup of the cache scheme, for example, as it had before. Nothing changes there. Build index now is a little different. Our index has word pairs. And we have this additional information that's the obfuscated location, Rn and Rn prime, Rn being the current and Rn prime being the next. This is then pushed through. We get pseudorandom labels as before, and encryption of the document ID and the location information here. Commas are concatenation. So the keys are the same, and the counter has the same meaning. The leakage is also very similar. Now, when Alice wants to run the token algorithm, she sends a phrase, say W1, W2, W3. She divides this into W1, W2, ends up with a token, saves that off temporarily. She then forwards W2, W3 to the token algorithm of Cash's system, outputs another token. These two subtokens are then forwarded as the token for the overall phrase. Now, when Bob runs search, he throws in the tokens, runs search of Cash's system on the EDB, gets some results. He stores those first results off to the side. That's the running copy of what is where the phrase exists in the document collection. He then takes the next token, runs that through, and ends up with a new set of documents. He now has to coalesce these two results to determine what documents contain both subphrases. He does this by comparing each new result to the old results. He sees the documents don't match IDs here, so he skips that one. Again, with 3, they don't match, so we can get rid of 4. It's impossible for it to occur. We then look at 3. This is the last element of the last token. So when we compare 3 to 9, 9 doesn't occur, so we get rid of 9. It can't occur in the phrase. We then look at 3. The document IDs match, and we'll also say that the location information matches, specifically R2 prime matches R4. So now we have our result of 3, which gets forwarded to Bob, and Bob can forward to Alice. The leakage here is a lot different. It's a lot higher. For example, it contains the leakage of both the subphrases, the leakage due to the documents returned, the search patterns of the two subphrases, and also all the location information, the obfuscated location information. So in conclusion, we presented a generic construction of searchable phrase encryption based on any CQA2 secure SSE system. The idea, again, was to make word pairs keywords and store location information as part of the document identifier. We had the cost of additional leakage, which is an open problem to improve this. It's non-trivial. And see our paper for additional constructions, including dynamic-based constructions. This is just the simplest one. Performance curves from implementation. We implemented 1 or 2 of these systems. The proof of the compiler theorem, if you're into proofs. And a discussion of leakage abuse attacks, which we're going to hear all about in the next talk. Thank you.